Next up, we have Kevin Wang, who will be presenting on lightweight traffic engineering for the AI ML fabrics, BGP Deterministic Path Forwarding, and Global Load Balancing. Kevin is a distinguished engineer at Juniper Networks and traveled from Boston, Massachusetts to be with us today. It looks like you have some Boston folks here. And this is Kevin's first time presenting. Welcome, Kevin.
Thank you. Can you show me how to advance the slide?
The green moves the slide, the green takes it back.
Okay, right. Thank you. Good morning. My name is Kevin Wang. I'm from Juniper Networks. So today I'm going to present lightweight traffic engineering for the AI/ML fabrics. I will present two solutions. The first one is Global Load Balancing, or GLB. The second one is Deterministic Path Forwarding, or DPF. I'm supposed to co-present this with my colleague, Mikhail, who is a product line manager from Juniper Networks. Unfortunately, he was not able to travel to Denver because of some unexpected event last minute. So I will also cover his part. So in this presentation, I will first talk about some of the facts about today's AI/ML fabrics, or my understanding about the facts. And then I will introduce the lightweight traffic engineering for the AI/ML fabrics. After that, I will deep dive into the two solutions. One is Global Load Balancing, and the second one is Deterministic Path Forwarding. So here are some of the key facts about today's AI/ML fabrics. We know they usually use the CLOS topology, and they use vanilla IP or IPv6. And usually, BGP is the only routing protocol used in these fabrics. The solution we are going to talk about are based on these assumptions. As we know, the AI/ML flows, they are usually high throughput and low entropy. This makes them very prone to congestion. On the other hand, these flows are not very tolerant for congestion. The reason is because those packet delay or loss in the fabric could lead to those AI/ML jobs to be either delayed or rescheduled. This will waste a lot of the very expensive GPU resources. So because of this, that's why the congestion avoidance is a very important topic, which pretty much every vendor is trying to solve in the AI/ML fabrics. The topic I'm going to talk about today is the lightweight traffic engineering. The solutions are IP-based, without MPLS, and they use BGP only. It works best under the CLOS networks. The first technology is BGP Global Load Balancing. This is an approach where you take your actual link node as an input and use it as a feedback to optimize your global load balancing decision, such that you want to optimize your node across all of the links globally, not just on your local links. The second solution is called BGP Deterministic Path Forwarding. This is trying to solve the same issue from a different angle. So unlike GLB, which is trying to reactively take in the traffic as a feedback to adjust, here we are trying to plan the traffic carefully so that you can avoid congestion from the beginning. So both technology, they can work independently. They could also work together. First, let's look at BGP Global Load Balancing. As we know, the random ECMP hashing, usually they could not make sure all of the links would have an equal node. In this example, let's say those two green flows from those GPU servers, as they come to leaf 1 and merge onto the link from leaf 1 to spine 1, it is possible to create a congestion on this link. In this case, because the link is local to leaf 1, so leaf 1 can detect this congestion very quickly and use it as a feedback to dynamically adjust its hashing. So that's why it's called dynamic node balancing. It's because the hashing algorithm is not static. It's not predetermined. It's actually taking the actual link node from the local link to decide how we are going to hash traffic. So based on this, once leaf 1 notices that the link towards spine 1 is congested, it can try to offload some of the flows towards the other two links, towards spine 2 and spine 3, so that it will help to mitigate the congestion on the link towards spine 1. So even though dynamic node balancing works great when you have the congestions locally, however, it will not help on those remote congestions. In this diagram, where let's say we have flows sending from leaf 2 and leaf 3 towards leaf 1 over spine 1, as these flows got merged on the link from spine 1 to leaf 1, they may create a congestion there. As you can see here, dynamic node balancing would not help on spine 1 because spine 1 only has a single link towards leaf 1. And there's really no alternative link for it to offload those congested traffic. And also, leaf 2 and leaf 3, dynamic node balancing would not be able to help either, because those links, local links on leaf 2 and leaf 3, they are not congested at all. So what we really need here is a technique called global node balancing, where spine 1 needs the help of leaf 2 and leaf 3 to offload some of the traffic going through its spine 1 towards leaf 1. To achieve this, leaf 2 and leaf 3 has to do two things. First, they have to be able to detect this remote congestion, because this link congestion is not local to leaf 2 and leaf 3. Just detecting this remote congestion itself is not enough, because leaf 2 and leaf 3 also have to understand the flow topologies. So they have to know, like, what are the flows which are actually using this congested link. So only those flows will be offloaded towards spine 2 and spine 3 to mitigate the congestion. So that's why there are two key important parts of global node balancing. First, you have to discover the topology of those flows. Second, you have to be able to detect those congestions which are not local to you. First, let's see how the topology discovery for global node balancing is done in a three-stage CLOS network. In this diagram, we have three leaf nodes, L1, L2, L3, and then three spine nodes, S1, S2, S3. To detect the topology, the flow topology for this three CLOS topology, what GLB has to do is, leaf 1 has to know that in order to reach leaf 2, if my next hop is A, then my next hop is X2. If my next hop is B, then my next hop is Y2. If my next hop is C, then my next hop is Z2. Similarly, L1 will also figure out, like, to reach L3, if my next hop is A, next hop is X3. If my next hop is B, my next hop is Y3. If my next hop is C, then my next hop is Z3. So as we can see here, in a three CLOS topology, knowing the next hop to next hop mapping will give you the complete path for each flow, because in the three-stage network, each route will only traverse two hops. So how can GLB discover this next hop to next hop mapping? As we know, today's BGP is really a next hop routing. So when a sender advertises a route, it only sends the next hop together with the route. So in order to know the next hop to next hop mapping, we need to enhance BGP a little bit such that it will carry a TLV for the next hop nodes together with the next hop whenever a router is advertising a route. Once the topology is discovered for this three CLOS network, The next step is to exchange the link quantity. That way, we can detect not only the local congestion, we can also detect the remote congestion. In this three-stage CLOS network, we let each spine to broadcast its link quantity to each of the leaves. So in this example, the spine S1, S2, S3, they will be sending the link quantity of the link X3, Y3, Z3 over the quantity message called QX3, QY3, and QZ3. Once leaf node L1 receives this remote link quantity, and also using the topology just discovered before in the previous slide, so now leaf 1 will try to use them to calculate the path quantity. For example, for the path going through S1 towards leaf L3, it goes through 2 hops. The local link is A. The next hop is X3. So using the quantity of A and the quantity of X3, L1 can determine the path going through S1. Similarly, using the quantity of B and the quantity of Y3, L1 can determine the path quantity of S2. And also using the quantity of C and the quantity of Z3, L1 can determine the quantity of the path through S3. Once the path quantity is determined, now leaf 1 can use them to adjust their hashing so that the node is balanced. For example, in this case, let's say if the link going from spine 1 to L3, link X3 is congested. So S1 will send the message QX3 to indicate that X3 is congested. Once leaf L1 learns this information, so he will know that the path going through S1 is more noded than the other path. That's how it can offload some of the traffic from link A towards B and C to mitigate the congestion on X3. To let the spine to send the link quantity information, we introduce a lightweight router information protocol, which usually runs on the packet forwarding engine side. It's a lightweight protocol, can exchange those link quantity within sub-milliseconds. Having shown how GLB works on the three-stage CLOS network, now let's see whether how it works on the more scaled 5-stage CLOS network. So here, we have a pod 1 and pod 2. Each of them is the 3-stage CLOS network. And then they are interconnected through those 2 super spines, SS1 and SS2. As we can see here, the intrapod GLB is really the 3-CLOS GLB, which we just talked about. However, to reach a node on the other pod, like in this case, for leaf L1.1 in pod 1, in order to reach those leaves in pod 2, like L2.1, so this is usually more than 2 hops. However, the solution only needs L1.1 to keep track of the 2 hops, first 2 hops, the next hop to next hop mapping. So for example here, to reach L2.1, if the next hop is A, then the next hop would be E and F. So here I miss a link for the link F, which is from spine S1.1 towards super spine SS2. And if the next hop is B, then the next hop would be G and H. So now let's see the next hop link E is congested. Spine S1.1 will notify leaf L1.1 about this congestion. Once learning that link E is congested, leaf node L1.1 will try to mitigate the congestion by offloading some of the traffic from link A towards link B. On the other hand, if a link I, which is more than 2 hops away from leaf node L1.1, if link I is congested, leaf 1.1 does not have to take any action. The reason is because GLB is not just running on those leaf nodes. It is also running on the spines, like spine S1.1 and S1.2 in this case. So when link I is congested, it is the next hop node of span S1.1 and span S1.2. So both of the spans will try to mitigate the congestion of link I by offloading the traffic from superspan SS1 towards superspan SS2. More importantly, because both spans S1.1 and S1.2, they are reacting to link I's congestion equally. So that's why NIF L1.1 does not have to prefer either of the spans. So now let's see how GLB works on the spines, like span S1.1 in port 1. Similar to like the NIFs, on the spine, it also keeps track of the next hop to next hop mapping. So in this case, from span S1.1, in order to reach NIF L2.1, if the next hop is A, then the next hop would be E and F. And if the next hop is B, the next hop would be G and H. So now again, let's say if the next hop E is congested, superspan SS1 will notify span S1.1 about the link quantity information. Once learning that link E is congested, S1.1 will know that this is the next hop corresponding to my next hop A. So he will know to offload some of the traffic from link A towards link B to mitigate the congestion on link E. Similarly, if link I, which is more than 2 hops away from span S1.1, if link I is congested, S1.1 does not have to take an action. The reason is because global load balancing is also run on those superspans SS1 and SS2. So in this case, since link I is the next hop of superspan SS1 and SS2, so both superspans will try to mitigate the congestion of link I by offloading the traffic from span S2.1 and span S2.2 towards span S2.2. And also because both superspans are reacting to the link congestion of link I equally, so that's why span S1.1 does not have to take any extra action for this link I congestion. So having seen how GLB works on the 3-CLO network and the 5-CLO network, now let's see whether it works for any stage of the CLO networks. Due to the rich redundancy of the CLO networks and symmetry of it, usually only the congestion of the next hop or the next hop links would affect the global load balancing decisions. Those congestions beyond the next hop, they are taken care of first by their previous hop using the dynamic load balancing. If that is not working, it will take action by the previous hop. They will use their global load balancing to mitigate the congestion. Since all of those nodes in the previous hop, they take the action equally. So that's why those hops, like 2 hops further before this congested link, will not need to take an action. So that's why each node only needs to track of the next hop to next hop mapping for the GLB topology. And also, it only needs to monitor the link quantity of the next hop and the next hops. So because of this design, it allows a non-link state protocol like BGP to be extended slightly to keep track of the topology. As we know, unlike those link state protocols, which usually keep track of every link in the network, BGP usually only keep track of the next hops. So with minor extension, it can also keep track of the next hop for each next hop. Also, because we only need to keep track of the next hop and the next hop, the link quantity exchange can be limited within those direct connect neighbors. This is very important because it can effectively avoid the flooding issue which IGP used to have in the CLOS fabrics. So for this requirement, when you receive a link quantity from your neighboring node, you only need to consume it locally. There's no need for you to further relay this link quantity towards other nodes. And as you can see here, the design is only counting on next hop to next hops. So that's why it works for any stage of the CLOS networks. There are two important parts of this global load balancing. One is for the topology discovery, and the second one is for link quantity or the remote congestion detection. To discover the topology, BGP need to discover the next hop to next hop mapping. So we have a draft introduce a new TLV called next hop node TLV under the existing next hop characteristic attribute. What this TLV is doing is it carries the next hop node towards the next hop node mapping information. So when a router is applies a route, it not only sends the next hop, it also sends this next hop node TLV together with the NHC attribute. Once the topology is discovered, we have another router information protocol. This is a lightweight UDP-based protocol, which is usually running on the forwarding engine, where it's the place you detect those link congestion. It's also the place you make your load balancing decisions. So because the protocol is really lightweight, it can allow you to exchange in sub-millisecond. Actually, the fastest rate could be as fast as about 40 microseconds. So having seen how GLB works, now let's use a simple test to further demonstrate the idea. To see how GLB can help to avoid congestion, let's first do the test without GLB to see how the congestion can happen in a case where it is technically avoidable. Let's start with a 90 gig of background traffic from spine 1 to leaf 2. And now we have a 17.5 gig flow sending from leaf 1 towards leaf 2. Without GLB turned on, leaf 1 would use the dynamic load balancing. The way dynamic load balancing works is it looks at its local links to decide where to hash the flow. In this case, since both local links do not have any traffic yet, so leaf 1 will just randomly pick up one of the link to send the traffic. In this case, let's say it pick up the link towards spine 2. Now let's add a second flow of 17.5 gig. At this point, leaf 1 is looking at both local links. He finds that the link towards spine 1 does not have any traffic, while the local link towards spine 2 already has 17.5 gig. So that's why the second flow is deterministically sent towards spine 1. So far, everything's good, but once spine 1 starts sending this second flow towards leaf 2, we will hit a congestion on the link from spine 1 towards leaf 2 because the combination of the red flow and the blue flow would be more than 100 gig of the link bandwidth. Now let's repeat this test with global load balancing turned on. So again, we have 90 gig of flow going from spine 1 towards leaf 2. And we have 17.5 gig of flow going from leaf 1 towards leaf 2. With global load balancing turned on, leaf 1 will not just use his local link node to decide where to hash the flow. He will use the path node to do that. So here, for the path from leaf 1 over spine 1 to leaf 2, as we see, the local link does not have any traffic, but the next hop link has 90 gig already. So that's why the path node is 90 gig, while the path node on the second pass over spine 2 doesn't have any flow yet. So that's why the first flow is deterministically hashed onto the link towards spine 2. Now let's add another flow of 17.5 gig towards leaf 2 again. So with GLB enabled on leaf 1, he finds that the left pass has 90 gig in combined, and the right pass has 17.5 gig in combined. So because of this, leaf 1 will figure out that the second pass is less loaded than the first pass. So that's why the second pass is hashed onto the link towards spine 2 again. So this shows how GLB can help to avoid the congestion on the link from spine 1 to leaf 2. The next solution I'm going to present is called BGP Deterministic Path Forwarding, or DPF. As I just explained, GLB is an approach which is trying to reactively take the link node and use it to adjust the hashing such that you would have a globally optimized link node to avoid congestion. Another approach to avoid congestion is like, how about if I can calculate those flows and I can carefully plan those traffic so that the congestion can be avoided from the first place. This is a proactive approach. As we know, traditionally, in the WAN network or some of the data center network, RSVPT is very good at planning traffic. However, in those data centers, the fabrics which you don't use MPLS or don't use RSVP, BGP DPF is an alternative approach to provide some limited traffic engineering. The idea of DPF is really simple. It tries to separate a physical IP fabric into multiple logical fabrics or conduit fabrics. Once a physical fabric is separated into multiple logical fabrics, the flow can be mapped to different logical fabrics for different purposes. You could do that for load balancing purpose. You could also do that to achieve different SLAs. There are also cases people use this to avoid fate sharing. So it's a lightweight traffic engineering under the IP fabric. So the way we try to separate our physical fabric into multiple logical fabrics is through BGP session cornering. Let's say in this simple example, we want to separate this physical fabric into two logical fabrics, a red fabric and a blue fabric. To do this, we corner the EBGP session on top of the link. For example, here, if I want a link from spine 1 to leaf 2 to be red, I just corner the EBGP session on top of this link as red. If I want to corner the link between spine 2 and leaf 2 to be blue, I just corner the EBGP session on top of this link as blue. Once the EBGP sessions are cornered with either red or blue, now we only allow a route to be advertised over these sessions or received over these sessions if the route kernel also matches the session kernel. For example, only those red routes can be advertised over the red session and received over the red session. Only the blue route can be advertised or received over the blue sessions. One exception is those unkerneled routes. They are allowed to match any kerneled fabric. The reason is for backward compatibility, and it's also for some cases people would want to use those unkerneled routes to go through all of the fabrics just for the protocol traffic only. Once we kerneled those EBGP sessions, now the next task is to kernel those routes so that we can tell the fabric like from which fabric I intend to advertise my route. The simplest way to kernel a route is just to give it one kernel. In this example, let's say leaf 2 kernel the route 10110/24 with kernel red, and the route 10220 with kernel blue. Once the route is kerneled, leaf 2 would be advertising the red route over the red sessions, the two red sessions with the red kernel community. And it will also advertise the blue route over the two blue sessions with blue kernel community. And once these routes are originated from those kernel fabrics, they will be routed exclusively over this same kernel fabric until they reach the ingress. Where on NIF1, we will see the red route will have two paths, both belong to the red fabric, and the blue route will have two paths, both belong to the blue fabric. So this is the simplest way people would make use of the DPF. The second way to count the route is sometimes people may want the route to use one fabric, but they don't want the route to totally fail when that fabric fails. They want a backup fabric to fall back. So in this case, let's say NIF2 count route 10110/24 with the primary count of red and backup count of green. So once this route is counted this way, NIF2 will advertise the route over the red session with the red community. It will also advertise this same route over the green session with the green community. In addition, we put an AIGP of 0 on the red path so that the receiver would know that the red path should be treated as the primary. So now when both paths reaches the ingress, NIF1 will have both the red path and the green path. He will know that the red path should be treated as primary and the green path as backup. So under normal case, NIF1 would be sending the traffic over the red path, but when the red path all fails, it will fall back to the green path. There are also cases people may want to count a route with all canals. In this example, let's say NIF2 count the route 10110/24 with all canals. What this effectively means, NIF2 will advertise this route over all of those canal fabrics, each with the corresponding canals. Like it's sent over the red fabric with the red canal, green fabric with green canal, green one with the blue canal, and purple with the purple canal. And once this route is received on the ingress, we will have a route with all 4 different paths. Each path will have its corresponding canal. This will give the ingress the full flexibility to decide which flow he's going to map to which next hop. The last way is also an important way to count the route is you count it with one canal with primary and all other canals as backup. In this example, NIF2 canal 10110/24 with red as primary and all other canals as backup. What this is going to achieve is NIF2 will advertise this route over the primary session with canal red. It will also advertise it over all other canals with the corresponding canals. Once this route, in addition, we also put an AIGP of 0 on the primary path. So once this route is received by the ingress on NIF1, you will have a primary path as red, and you will also have backup paths of green, blue, and purple. So why do we need to do this? The reason is because when NIF1, under normal case, he wants to send the traffic over the red fabric. In case the red fails, if you only have one canal to protect red, then all of the red traffic suddenly goes to that canal, let's say go to green. And the green also has its own traffic. When you have green fabric to carry 2 fabric traffic together, it can easily cause congestion there. So that's why we are trying to spread the red traffic towards all of the remaining fabrics as protection. This is done through ECMP, and if the network is provisioned with reasonable amount of headroom, usually they could absorb this red traffic without causing any additional congestion. As we can see here, there's 2 parts of DPF. One is to configure, to count the session. The second part is to count the route. So to count the session, so here I'm using the Juno's CLI example to see how session can be easily counted. It can be counted at all 3 levels through the fabric count command, where let's say if a node is only participating into one of the count fabric, then we could just count this entire protocol BGP as one fabric kernel for this node. On the other hand, if the node is participating into 2 different fabrics, let's say it has both blue and red, what we can do is we can group all of those blue sessions together and count the group with blue, and group all of the red sessions together and count the group with red. It is usually not necessary to count the session individual one under the neighbor level to minimize the config. Once the sessions are counted and the fabric is partitioned into multiple counted fabrics, now the task is to count the route. So this can be done through a single command called fabric advertise. With this command, you can specify a route, and you can specify a kernel, or optionally, backup kernels. So far, we have talked about how DPF is implemented and how it can be configured. Now let's see a couple of use cases to see how DPF can be used to achieve the goals we are talking about. The first use case is called QPL pinning, or QPP. For those of you who are familiar with RockV2, you know that when those GPUs want to exchange their data with each other across the fabric, they would use the RDMA, and the RDMA allow you to partition a big chunk of data into equal amount of smaller data, and each of them will be assigning a QPL so that you would have the same big chunk of data sent through those QPLs to increase the entropy. So in this case, let's say if we have a fabric with 8 spines, if we partition this fabric into 8 logical fabrics, each with its own kernel, and we also partition the QPLs into 8 QPLs, because each QPL would have equal amount of data, and if we map each QPL deterministically into one of the kernel fabric, in theory, we can guarantee that each of the uplink would have equal amount of node, and then you would never experience congestion here. The next example is for the GPU as a service, in the case where you may have a fabric which is rented, and your GPUs are rented towards multiple tenants. And in this example, you have a red tenant and you have a blue tenant. So for whatever reasons, they may need different SLAs. Either they don't need so much or they are not willing to pay so much, right? So it might be desirable to let the red customer traffic to go through the red fabric and the blue customer traffic go through the blue fabric. This way, they could achieve different SLAs. It's also possible to isolate their traffic so that they won't interfere with each other. A third use case is avoid fate sharing. In this example, a physical fabric is partitioned into 3 logic fabrics. We have a red fabric, a blue fabric, and a green fabric. So in cases people may want to map their exception flows towards the green fabric to avoid fate sharing with the ordinary flows which go through the red or blue. There's also another interesting case which is less related to AI/ML, but it's a real case where people want to use the parallel redundant protocol to replicate their packets for their mission-critical packets. One example is those packets could be used to control those robots in the factory. You want the maximum redundancy, and you don't want any single point of failure. So in this case, if we have this logical fabric, it is possible to map one copy of those redundant packets over the red path and the other copy over the blue path, so that they will go through those disjoint paths without fate sharing, so that you can avoid single point of failure. So far, I have talked about how GLB and DPF, they work independently to achieve their own traffic engineering. It's important to note that they could also work together in a lot of cases to get even better traffic engineering. So coming back to this example, the multi-tenancy example I have just talked about, where DPF is used to map the red customer towards the red fabric and the blue customer traffic towards the blue fabric, right? This is using DPF. But if you look at one individual fabric, like the red fabric or blue fabric, you also have multipath and load balancing at each hop. So if you enable global load balancing, it can help to optimize the link node within each of the kernel fabric this is an example where both technology can work together to maximize your traffic engineering and avoid convergence, avoid congestion. There are also other examples which I'm not showing here. So the way I look at these two technologies, like DPF is more like a proactive planning approach where you calculate the traffic, you plan it carefully so that you avoid congestion from the beginning. This could work very well for those simple topologies, like the three-stage CLOS network, where in the example of the QPL pinning example, you can carefully plan the traffic so that you can guarantee each of the uplink would have an equal node, right? However, when the network is getting larger, getting more complicated, like modern days hyperscaler, you could have 100K GPU, thousands of nodes, right? In those cases, it's very hard, if not impossible, to pre-plan the traffic such that you make sure each link to have equal node to avoid congestion. So in those cases, again, we can take this hybrid approach where you may want to use DPF within your 3-CLOS pod, within your intro pod, you use DPF to carefully plan your traffic so that you would never hit congestion there. And for those interpod traffic, which are hard to plan, you can use GLB, Global Load Balancing, to reactively adjust your node, adjust your hashing based on your actual traffic node. So here's the summary. We know like AIMF nodes, they are very prone to congestion, but they are less tolerant of congestion. And global load balancing is a reactive approach which helps avoid congestion, try to optimize it globally so that you have every link has equal node or close to equal node to minimize the congestion. And then the BGP Deterministic Path Forwarding is a technology where you proactively plan your traffic to achieve different SLAs or to avoid congestion and avoid fake sharing. And we have both technology there. They can be used separately, or they could also be used in combination to achieve traffic engineering. And it's also very important to know that both technologies, they achieve traffic engineering without losing the simplicity of today's AIML fabrics, which is to use the CLOS topology, to use vanilla IP or IPv6, and to use BGP as the only routing protocol. All right, so this will conclude my presentation. Thank you.
Thank you very much, Kevin. All right, I see folks lining up already. Please state your name and the company you're with, and then go ahead with your question. We'll start with you.
No new TLV. A question about whether you've done any NS3 or similar types of simulation in order to validate the behavior of the GLP operation. You have two control loops operating kind of simultaneously, and it would be good to know or interesting to know whether what's happening on the data plane with simulated AI workloads is actually reflective of what you're doing in the control plane here.
Let me try to confirm the question. So you are asking about simulation for GLB, right? Or both GLB and the DPF.
Right.
Okay. Yeah, actually, we at Juniper, we have an AML lab where we use those AML jobs, benchmark jobs, to do the simulation. It's not really a simulation. Those benchmark jobs are running in the fabric. And we applied different technology, like for the global load balancing unknown, we can see that in a congested network, we can increase the fabric utilization by 35% or even more. And if you translate towards the job completion, we could also see the jobs are completed much faster with global load balancing enabled. And also for the DPF use case, like the QPL pinning case I was talking about, we have seen similar result. I mean, like we have seen like 20%, 30% improvement with this kind of planning.
Cool. it'd be great to see those simulations presented at a future NANOG.
Yeah, so those are going to be published as part of the marketing effort. It's not here.
Hello, Aaron Atach, Akamai. I read the draft regarding exchanging link quality information for GLB, and noting that it's based off UDP, I didn't see any mentioning in the draft about what if the receiving node fails to receive the message for whatever reason.
Okay. So let me try to understand the context. Are you talking about the multi-vendor case, receiving node failed to receive, or you just talk about the failure, like the
just general failure, and like
just
what would be is there any like retry mechanism or?
Right. No, so these, as I said, these are the lightweight UDP messages. They are exchanged at a really fast rate. I said sub-millisecond, but in reality, they can go as fast as microseconds. So if you lose a packet, it's fine. You would only have an issue, let's say, if you lose the packet for a few seconds or something, then your congestion could start to build up. So I was showing those as congestion, but actually, these are the proactive approach where we don't wait until the link is congested before you take action. We look at the queue, like if the link quality is dropping below a certain threshold, we start to offload traffic towards other links which has less load. So if you lose one or few packets, it's fine.
So link quality information is constantly being sent?
Yeah, it's constantly sent in the fresh.
Thank you.
It's either constantly or like if it's not changing at all for a long period of time, we may reduce the rate. But in general, it should be able to tolerate several failures.
Thank you.
Hello, Patrice Brissette from Cisco System. Thanks for the presentation. Quick comment is about the performance. It would be very interesting if you can have shared the various performance based on the training versus inference versus RAG and a big mix of all of that. Because right now we don't know. We're kind of in the blind with this presentation.
Okay, so once, you can contact us offline. So once we have those data, I think right now these are all very new technologies. We have just developed, like GLB is just the first release was last year, and this year we are extending it towards the more scaled, like scale up to 100K GPUs, right? And for the DPF, it's again a new technology. We are just releasing in the currently. So the marketing data is going to come slightly later. Yeah, contact us offline, and we will provide you those data.
Hello, Prabhakar Nagral from Siena. Thank you for the presentation. So 2 questions. You talk about the router information protocol. Is it a new protocol altogether?
Yeah, it is a new draft under IETF. And the way we are doing this is trying to standardize that so that in the future, it is possible for inter-vendor to interoperate. The different vendors can interoperate even within this data center fabric.
Okay. And second question is the traffic engineering, this is done purely based on at the node level because there is no external controller involved or anything, right? This is purely done at node level.
Are you talking about global load balancing or?
The overall lightweight traffic engineering, right?
Yeah, so for global load balancing, as you can see here, the draft is called next of node. It is really node level. The reason we only care about the node is because when you have, a lot of cases, the CLOS network, you don't have parallel links, but if you do have parallel links, those links sometimes are bundled as a single link, or even if you are not bundling them as 2 parallel links, the forwarding engine can report the link, the aggregated link quantity for these 4 links together, the parallel links together. Because usually if you have a congestion on one of the parallel links, right? So the dynamic load balancing on the node itself will be able to react really quickly to adjust the node so that you have an equal node. The global load balancing only kicks in when the local dynamic load balancing cannot help. Either like, for example, for the 3 CLO or 5 CLO, the last hop, as you can see, is a single link. If that hop is congested or fail, there's no way he can do that. So that's only those cases we will propagate to previous node. So that's why the previous hop only cares about the next up node. It doesn't really care about those individual links. And a lot of cases, you don't really have many individual links It's usually just a single link.
Okay, thank you.
Thank you.
Any other questions? All right, I think that was it. Kevin, fantastic job. Thank you. Let's give a hand for Kevin.